let us continue with the light-like particle motion in the Schwarzschild background. So we have obtained the following geodesic equation for the geodesic in the Schwarzschild spacetime, which is as follows: m squared rg divided by 2l squared plus 3rg over 2u squared. So this is for the massive particle motion, but for the massless this is 0. So we obtain the following equation for the massless particle: d squared u over d phi squared plus u is equal to 3rg over 2u squared. Again, we consider this term as a perturbation. So we, in the Newtonian limit, the equation that we have, so in the Newtonian limit, the equation that we have is as follows: du squared over d phi squared plus u0 is equal to 0. And the solution of this equation, obviously, is u0, which is equal to 1 over r0. Again, 0 subscript corresponds to that. This is Newtonian limit, leading approximation. The solution of this equation is just 1 over a cosine of phi plus phi 0, where a and phi 0 are some constants. This expression defines as a line in the plane. So if we have a plane with the coordinatization, which is r0 and phi, so this defines a plane. Indeed, let us consider it. So this is just a, this is just phi 0, and this is a situation that we have r0 and phi. So, I mean, this was just to picture it. So in reality, we have the following situation. So 1 over, well, then one can see from this picture, from this rectangle, one can see this relation. And indeed, one can see that as phi plus phi 0 goes to pi, r0 goes to infinity. So as this argument goes to pi, r0 goes to infinity. Now we want to find, acting as in the case of the massive particle, we want to find u1, and the equation, so we have to substitute u0 to here, and then we obtain the equation for u1. So d squared u1 d phi squared. So this is a first relativistic correction. u1 is equal to 3rg divided by 2a squared cosine squared phi. The solution, so we, for simplicity, put it phi 0 to 0. So the original initial phase. Then the solution of this equation is 1 over r1, which is u1. So this is u1, is equal to rg divided by 2a squared 1 plus sine squared phi. So this is the solution for this equation. So for the light-like particle, we have obtained that 1 over r0 is 1 over a cosine of phi. So remember that we put phi 0 to 0. Then this corresponds, let me draw the picture, this corresponds to the straight line, straight vertical line, where this distance is a, straight vertical line. Now, if we take into account relativistic correction from general theory of relativity, 1 over r0 plus 1 is approximately, of course, 1 over a cosine phi plus Rg divided by 2a squared 1 plus sine squared phi. And now we have the following thing. While when phi is equal to pi over 2 plus minus, we have R0 going to plus minus infinity. So that corresponds to going there and there. Now here we have a little bit different situation. R0 plus 1 goes to infinity at phi equals to plus minus pi plus some small angle alpha. So this guy, well, sorry, to plus infinity, of course, here. So R0 becomes infinitely large. This goes to plus infinity, where this small angle alpha solves the equation following from here. So minus 1 over I, a sine of alpha, so I just plug this here, sine alpha plus r g over 2a squared 1 plus cosine squared of alpha equals to 0. So alpha solves this equation. So when this becomes 0, R0 goes to infinity. Approximate solution of this equation is alpha approximately equal to Rg over A. So we have the following picture. Light ray is deviated by the following situation. So we have alpha deviation here and alpha deviation here. Alpha deviation here. So as a result, if we are, like for example, if we have a star here and looking here, we see the star as if it is present here. So the deviation is by the angle 2 alpha. As a result, the total deviation is 2 alpha, which is 2 Rg over A. Now, for the case of the sun, we have that Rg for the sun is approximately 3 kilometers, 3 to the 10 to the third meters. At the same time, its actual radius is approximately 700,000 kilometers, which is 7 to the 10 to the 8 meters. From here, we obtain that this is, for the case of the sun, this is approximately 1.75 angular seconds. And this effect was observed in 1919. And that was the beginning of the era of the general theory of relativity, when it was considered as being proved by this experiment.